Thank you for the introduction. So today I'll be presenting the threat class predictor. So this is an approach that was done by myself and Serge-Oliver Paquette. We're both data scientists at SecureWorks. All right, there you go. So yeah, just a rough agenda. I'll be presenting the semantic representation of vulnerabilities that we use then to build a threat score and then a trend score. And following this, we combine these in a visual dashboard and we'll follow up with discussion and conclusion. So the general goal of this approach is to build an explainable machine learning framework that can predict threats linked to newly disclosed vulnerabilities. So here, essentially, with new vulnerabilities that come out, we want to know which ones are more at risk of being the victim of threats, to essentially know which vulnerabilities might be truly critical, which vulnerabilities to patch first, and so forth. And to do this, the first step we do is to build a semantic representation of historical vulnerabilities. So as we all know, when vulnerabilities are disclosed, when they come out and they're published by the NIST, one of the big information part with vulnerabilities is the vulnerability description. So we've decided to use a topic model approach to build topics around historical vulnerabilities to have a semantic representation and essentially be able to use the description to build models. So we use topic modeling, specifically LDA, latent directly allocation, which is probably the most popular topic modeling approach. And essentially, topic modeling is unsupervised machine learning. So it's essentially clustering documents into global topics, concepts, and so forth. And in our case, documents are vulnerability descriptions. So we do the typical NLP shenanigans. We remove stop words, we remove common words, and we lematize the words. And then we train a topic model on all vulnerability descriptions. Now, we do have to specify the number of topics we want with LDA. So we tried multiple number of topics and we got the best coherence with 30 topics. So we went with 30 topics. And the good thing about using topic models is that we can simply look at the actual topics with word clouds to quickly understand what the topic is actually about. So LDA finds latent hidden topics, but we can simply look at the topics. So for example, I have 3 topics on the slide that are from our build model. And looking at them, we can see that the first one is heap and buffer flow vulnerabilities. The second one is more parameter SQL injections on plugins. And the last one is cross-site scripting. So another thing, we do get global topics with LDA, but another good thing is that we get vectors for every document used to train the model. Essentially, a vector of 30, indicating for a specific vulnerability description, which of the topics are more relevant. So this is just an example topic, one of the 30 topics generated by the model. So it's very simple. We simply have weights with words, and we can look at this with a word cloud to understand really what it is about. Now, using this semantic representation, we can then use the actual vectors we have for every vulnerability description as input to other machine learning problems. In this case, what we'll try to do is to do threat prediction. So threats in the sense of malware might use a CV in a short while, or maybe there's exploits that might come out for the vulnerability. So we want to predict these ahead of time so we can patch them before the actual attack. So in this case, we have multiple threats that aren't mutually exclusive. So essentially, we have a multi-label problem. For this reason, we've decided to train a binary model for every threat class. So we have multiple models, and we simply combine the output to identify all the threats, if any, that might target a new vulnerability. So we use the topics as input features to the model. So essentially 30 features, and we also combine it with general features of the vulnerability, essentially the information we get when a vulnerability is just published. So we use, and this is based on prior work. Essentially, we use the length of the description, the number of affected software, the number of references, and the CVSS2 score and metrics. The vulnerabilities used to train the model are all the vulnerabilities published on the National Vulnerabilities Database from the NIST from 2008 and up. So the vast majority of vulnerabilities. Now for the labels, we've implemented the approach using two types of threats: the publication of exploits for a vulnerability and the inclusion or the use of a vulnerability by malware. So that we do need labels for this. This approach is a classical supervised machine learning approach. It's pretty straightforward. We use topics, features from the vulnerability, we have labels, we predict if an attack will come. So for the actual labels, for the exploits, we use publicly accessible public exploit repositories like ExploitDB, Paquette Storm, and proof of concepts on GitHub. And for the malware, we've used signatures from ClamAV. So ClamAV is an open source antivirus engine. So we do have access to the signatures, and we simply look, is there a CV in the signature? If so, we have a label set to 1. And we also combine this with internal SecureWorks malware reports from the counter threat unit. So we have the actual number of samples in the table on the right. So you can see we have around 150,000 vulnerabilities, but we have a lot less exploits and even less malware samples. So we're faced with an unbalanced data set in terms of labels. So to manage this, we've combined two approaches. So we use class weights when training the actual model to give more weight to the minority class, since that's specifically what we want to predict, new attacks. And we also use threshold moving on the output probability of the model. Essentially, instead of doing 0.5 to decide if it's 1 or 0, we change it around to essentially boost the recall in our approach. So the setup, the evaluation setup is pretty straightforward. We use tenfold cross-validation. We did a grid search. We did a grid search, find the parameters. We use a random forest classifier. We did compare with SVM and logistic regression, but the random forest classifier got the best results. And this is all done in Python and sklearn. And the grid search parameters are on the right for those that are interested in this. We do have different parameters for different threats, since, as I said before, we have a model trained for every threat class. Now, the metrics we'll be looking at in the results are specifically the accuracy, the recall, and the F2 score. Now, we look at the accuracy to get a general sense of the model, but since it's an unbalanced problem, we also look at the recall, specifically more than the precision, since in our case, we want to know, we want to optimize to identify true attacks at the expense of false positives. So essentially for, let's say for some of our clients, if we miss an attack, it's a lot more damaging for a client that if we simply give false positives that maybe take a bit more time for analysts, but there's no missed attack. So these are our results for the two classes. So we have results for the prediction of exploits and for the prediction of malware inclusion. So when doing exploit prediction, we have around 88% accuracy with close to 80% recall. So the model does great at identifying true attacks, we can see though that the precision goes down. So we do identify true attacks, but we have some false positives. And when we look at the prediction of CVs that might appear in malware, the results are even better. We get 98% accuracy with close to 88% recall. So it does great. And again, the precision is lower. So we do get some false positives. So yeah, we have the threshold as well. Now, one important aspect is that, as I said before, we have some labels for exploits and malware, but our data set is incomplete. Essentially, we don't have every exploit that used every CV ever. We do have a good chunk of them, I think, through ExploitDB and the other sources, but we don't have all of them. And that's even more true for malware. It's really difficult to know every CV that was used by malware. So essentially, our data set for labels is incomplete. So a lot of the false positives we get are actually true positives that we simply don't have in the data. So the precision is artificially lower than the actual true number. Now, this is for the predictions of threats. Now, we went a step further in using the topic model, and we now try and identify a trend score linked to vulnerabilities. So we have a topic model trained on vulnerability descriptions. And what we've done is we simply apply this model to online discussions, essentially tweets on Twitter that mention vulnerabilities, Reddit posts, and dark web forum posts. And we simply apply the topic model to all of these posts, essentially getting a vector of 30 for every post where the numbers are which topics are relevant to this specific post. We average the whole lot to get a final average vector of essentially which of the topics of our vulnerability topic model are currently trending in online InfoSec discussions. So this is what we call the trends. And we do average these over 30 days to get more stable trends. So we do a rolling average. Essentially every day we capture a number for the last 30 days to get the sense of how the trends are evolving over time. And then with these trends, we have a vector of 30 numbers for the trends. And as I said before, with the topic model, we do get a vector for the topics for every vulnerability description. So using this, we can link back to our vulnerabilities by simply doing a dot product between the trends and every vulnerability description to get what we call a trend score. So we multiply the weight of topic 1 for the vulnerability and the weight of topic 1 in the trends. And we do this for every topic. We sum the whole lot. We get a final value, which we call a trend score, which essentially the higher the trend score, the more closely this vulnerabilities topics or concepts will match what's being discussed online. Now with this trend score, we can combine it to the threat score in what we call a visual dashboard. So this is, for now, it's simply a plot where we've run the approach for a month in July, and this is the results we got. So essentially, we just plot the threat score on the y-axis and the trend score on the the threat score on the x-axis and the trend score on the y-axis. And with this representation, what's interesting is that if we look at the different parts of the visual dashboard, we get very different signals. For example, if we look at the top left, we can see vulnerabilities that match highly with what's trending online, the InfoSec discussions, but aren't really likely to be the victim of threats. So these vulnerabilities might not be as important as you could imagine at first. But then if we look at the top bottom right corner of the visual dashboard, we get the opposite. We get vulnerabilities that are likely to be the victim of threats or targeted by malware or exploits, but do not really match what's being discussed online. So these are particularly important for us. And we think that's the vulnerabilities that we might want to prioritize first, because they're the vulnerabilities at risk of going under the radar and being missed by security analysts. Now, these are just 3 examples took from the run we did in July. Essentially, there's one vulnerability that was predicted successfully to have exploits come out, a second vulnerability that did appear in malware after the fact, and we can see, I don't know if we can see, it might be small, but they're on the plots in orange as well. And we can see the last vulnerability is so the first vulnerability is a SQL injection on Django, and the second one that was used in malware is a privilege escalation on Windows. And that was actually a small description, but it was still picked up and correctly identified. And the last vulnerability is a remote code execution that was really matching what was being discussed in July, but it wasn't actually predicted to be in threats. Now, I did say at the beginning that this was an explainable machine learning framework. So for the trends, it is pretty self-explanatory. Essentially, we can look at the top trends and understand what's trending, what's not. And we can do something similar with our vulnerability threat score, because we've used the topics as features. So we can simply look at the top features for different types of threats and understand how the model predicts threats, different types of threats. So we did this for exploits and malware. For exploit, looking at the top features, we see it uses the references heavily. So more references will be more at risk of being having exploits come out. But it does also use a bunch of the topics. Specifically, it uses parameter and SQL injections. It's a topic on the right. It also uses Google and OAuth vulnerabilities. And there's also the topic of cross-site scripting and denial of service. And these all make sense when predicting exploits. It's the kind of vulnerabilities that often have exploits published for them. But we can also do the same thing for predicting malware. And when predicting malware, we get completely different topics. Here, now we do get vulnerabilities that are linked to Windows handles. We get PDF vulnerabilities, and we also get heap and buffer overflows, which makes sense. It's the kind of vulnerabilities that malware used to infect machines. And the word cloud on the right is the top topic again. So that's the general gist of it. We have a semantic representation that we use to build a threat score to predict threats linked to vulnerabilities. And we've combined this with a trend score in a visual dashboard to see which vulnerabilities might go under the radar of security analysts and which vulnerabilities might be more prioritized. So thank you, and I'll take questions now.